In this video, we're going to review how to solve problem 4-75. So in this problem, we'll approach it just like the others. We'll start by first creating a free body diagram with all of our loads identified. So first, we'll sketch our beam as a straight line, and then we'll identify all the loads on it, and we'll break loads into X, Y components. So first, we'll start by identifying those. Well, we'll start at the left here. At point A, we've got a load. We've got a roller, so we've got a load pointing down at A. Then we've got a 50 kilonewton load pointing down at this point. At B, we have two forces. We've got a horizontal, we'll call BX, and we've got a vertical load, we'll call BY. Because that's a pin joint, we can have both loads. And because this beam is not a coplanar parallel system, our 85 kilonewton force is at an angle, so it's not all parallel. We have forces in both X and Y direction, so we need to include the BX in this example. Lastly, we'll include the 85 kilonewton force. So I'm going to draw that first in this color, because we're going to, as I said, break it into its X and Y components. So to do that, we have a Y component like this. Our force is at an angle 8, 15, which would make this 17, and it's 85 kilonewtons. So we're going to have a vertical component and we're going to have a horizontal component. Our vertical component is going to be equal to 15 over 17 times 85 kilonewtons. So we're using similar triangles. We know that this 8, 15, 17 triangle is similar to the triangle that includes the 85 kilonewton force and the X and Y component forces. So our 85 kilonewton vertical force will be 15 over 17 times 85. And that is equal to 75 kilonewtons. And our horizontal force will then be the 8 over 17 times 85 gives us 40 kilonewtons. So now we've identified all the forces on our free body diagram. We broke them into our X and Y components, and we will label our dimensions. We'll go to point B in this case. So we've got 6 meters to the force at A. We've got 2 meters from B to the 50 kilonewton force, and then we've got 6 meters out to the 85 kilonewton force. And the reason we're going to do that is for our equilibrium equations. You can always recalculate whichever distances you need, but we're going to set up our equilibrium equations. So we'll start, because we've got this beam problem, we'll start with our sum of moments. And because we've got two forces at B, we're going to start with the sum of moments about point B is equal to 0. And that's going to be counterclockwise is positive. Our equations for this Our horizontal forces go through point B, so they don't create any moment, but force A creates a moment in the positive direction. So we'll have A times distance of 6 meters plus 50 kilonewtons times a distance of 2 meters minus 75 kilonewtons times a distance of 6 meters. That's equal to 0. So we have A is equal to 6 times 75 minus 50 times 2. And that is divided by, so that is 350 kilonewton meters, and we'll divide that by 6 meters, and that will give us 58.3 kilonewtons. At A. So we'll write in here 58.3 kilonewtons. Now we can do either one next. We'll start with the sum of forces in the y direction is equal to 0. So we have minus A, which is 58.3 kilonewtons, minus 50 kilonewtons, plus By minus 75 kilonewtons is equal to 0. And that leaves us with By is equal to 58.3 plus 50 plus 75, 183.3 kilonewtons. Okay. So next, we'll do our last equilibrium equation. We'll do sum of forces in the x direction is equal to 0. In the x direction, we have Bx, and we have a negative 40 kilonewtons because it's pointing to the left. That's equal to 0. If we solve that for Bx, we get Bx equals 40 kilonewtons. Now we've found all of our unknown forces, and we've completed the problem.